Hello everyone, my name is Amira Faqihah Binti Mahmod from AS2026A1. In the requirement to complete the assignment of CHM 678 Material Chemistry, me and my friend will present on Chapter 7, which is Phase Diagram, Isomorphous and Eutectic. So basically, in this topic, we will learn about phase diagram for alloy system is important because there is a strong correlation between microstructure and chemical property. Second, development of microstructure of an alloy is related to the characteristic of its diagram. Third, for many alloy systems and at some specific temperature, there is a maximum concentration of solute atom. Solubility is a physical property, the maximum amount of solute that can dissolve in a solvent at equilibrium which produce saturated solution. For example, in solution, sugar is dissolved in water. In solid solution, diffusion of small number of P atoms into single crystal silicon. And lastly, in air, which is oxygen is soluble in nitrogen. Unlimited solubility or complete solubility means only one phase is produced with unique property and composition different from initial phase. Liquid Cu plus liquid Ni, when solidified, only one solid phase is produced. After solidify, the Cu and N atom do not separate but randomly located within the FCC crystal structure. No interfere exists. For example, water and alcohol are soluble into others. Unlimited solubility regardless of the ratio of water and alcohol. The condition for unlimited solubility, in order for an alloy system such as copper nickel to have unlimited solid solubility, certain conditions must be satisfied. These rules are the Hume's rotary rules. There are four types of Hume's rotary rules for the formation of substitutional solid solution. First is the relative size factor. Diameter of the atom of the metal must not differ by more than 50%. Second, crystal structure factor. The two elements should have the same crystal structure. Third, chemical affinity factor, not much difference in electronegativity. And lastly, valence factor, the two elements should have same valency. This is the calculation for the atomic radius difference. Atomic radius difference equal to final radius minus initial radius divided with initial radius and times with 100%. We will see the example on the next slide. Next, we will see the Cu and I system. In this table show 5 different elements, which is copper, zinc, nickel, silicon and aluminium. For each of the element is located at different part in the periodic table. Copper is located at group 11, zinc at group 12, nickel at group 10, silicon at group 14, while aluminium at group 13. For the radius, aluminium show the longest radius, which is 0.143. For the crystal structure, copper have the FCC structure, which is face-centered cubic. Zinc have HCP, which is hexagonal close pack. For nickel, also FCC. Silicon is diamond cubic. Aluminium also FCC. Copper show an high electronegative value, which is 1.9, because copper has only one valent electron at the outermost shell, so the electron can easily be removed from the nucleus as the force of attraction between the atom and the valence electron is weaker. And for the last columns is valence. Valence is the property of an element that determines the number of other atoms with which the element can be combined. Next is this table show the system of Cu is being compared from 4 different elements, which is zinc, nickel, silicon, and aluminium. First is the atomic radius difference. It can be calculated from the formula that I have mentioned before. The CuNi system has a very high predicted degree of solid solubility, as the atomic radius difference value is the lowest, which is 2.4. Thus, it will lead to higher value of observed solid solubility, which means when atomic radius difference lower, so the percent of observed solid solubility is higher. Limited solubility or partially solubility, more than one phase is produced, each with unique property and position. Small amount of salt to water will become salt solution and become in one phase. Too much salt in water, the solution will become saturated. Excess salt will sink to the bottom of the glass, so it will become two-phase. For example, saturated solution of salt and the solution of copper zinc. Liquid Cu plus with liquid zinc, unlimited solubility for zinc less than 30%. First, for amount of zinc less than 30% of total composition will become one phase. Second, after solidification, single solid solution have an FCC structure result with Cu and zinc atoms randomly located at the normal lattice point. Next is limited solubility for zinc more than 30%. For zinc more than 30% of total composition, it will become more than one phase. Second, therefore, the solubility of zinc in copper is limited. A solid solution of copper saturated with about 30% zinc and a CuZn compound. Some of the existing atom combined with some of the copper atom to the CuZn compound will become two-phase and now coexist. Now we will move on to phase diagram. Phase is a region in a material that differ in microstructure and composition from other region. Phase diagram, a graphic representation of the combination of temperature, pressure, composition, or other variable for which specific phase exists as equilibrium. Indicate equilibrium solid solubility of one metal in another. Indicate temperature range under the solidification occurs. Indicate temperature at which different phase start to melt. There are two types of phase diagram. First is one component system, which is pure substance, water. Second one is two component or binary system, which is isomorphous, example copper and nitrate, and eutectic, example plumbum and Sn. The diagram shows the phase diagram of water. It has three different phases, which is solid, liquid, and gas. It also have three different points. First is triple point. Triple point is where the temperature and the pressure of the solid, liquid, and vapor phase of the particular substance coexist in equilibrium. Next is critical point. Critical point is a point which both liquid and gas phase of a substance have the same density and the endpoint of the phase equilibrium curve. Lastly is supercritical fluid, which is any substance at a temperature and pressure above its critical point where liquid and gas phase do not exist. Next, we will see the two-component or binary system, for example, copper and nitrate phase diagram in isomorphous. It has a complete liquid solubility and complete liquid solubility. It has the same crystal structure for all the composition. The graph shows the copper and nitrate phase diagram. From the diagram, we can see that solid placed at the bottom part, while liquid placed at the above part, and in the middle is the combination of liquidus plus solidus. There are 6 interpretations of phase diagram: 1. Solidus, 2. Liquidus, 3. Overall composition, 4. Chemical composition in two-phase region, 5. Determine the amount of phase in two-phase region, and lastly 6. Development of microstructure. That's all from me. My friend will proceed to the next slide.
Hi, Assalamualaikum. My name is Mahmod Ghazali and I will continue the slide chapter 7, which solidus and liquidus. First of all, solidus is also known as solidus line, is that below which the solution is completely solid and does not contain a liquid phase. The temperature at which liquefacting begins. Meanwhile, the liquidus is known as liquidus line. It separates the liquid phase from solid or solid plus liquid phases. That is, the solution is liquid above the liquidus line. The temperature at which solidification begins. This is the overall composition of a mixture at any given temperature. The diagram has axis Y, which temperature, and axis X is composition. In this diagram, we can determine the liquidus line and solidus line. This diagram has 3 different phases region, which the alpha region, the liquid region, and the alpha plus liquid region. For example, at the position A, 41,150 is alpha, and at position B, 27,1,200, it is alpha plus liquid. Next, it is finding the composition in a two-phase region. First, locate composition and temperature in diagram. Second, in two phases region, draw the tie line or isotherm. Third, note intersection with phase boundaries. Read composition at the intersection. 4. The end of the tie lines represent the chemical compositions of the two phases in the equilibrium. The tie line is connect the phases in equilibrium with each others. That's also sometimes called an isotherm. The compositions of each constituents will be determined at point B. Draw a horizontal line at the given temperature, Tb, from the first phase boundary to the second phase boundary. The composition of the liquid phases, Cl is 32 with percent nickels to 68 Wt percent copper. Thusly, the alpha phase CO has a composition of 43 Wt percent nickels to 57 Wt percent copper. Next is finding the amount of phases in a two phases regions. Use lever rule. Fraction of a phase is determined by taking the length of the tie line to the phase boundary for the other phase and dividing by the total length of tie line. You can use WL equals ML over ML plus M alpha equal to S over R plus S equal to C alpha minus CO over Ca minus Cl. Then you can look to other examples. Next is development of microstructure in isomorphous alloys. First, solidification in the solid plus liquid phase occur gradually upon cooling from the liquidus line. Second, the composition of the solid and the liquid change gradually during cooling, as can be determined by the thin line method. Nuclei of the solid phase form and they grow to consume all the liquid at the solidus line. This is the diagram that shows the development of microstructure in isomorphous alloy. The next slide is cooling of the copper nickel alloy.
Next, we move to the cooling curves. Cooling curves is the alloy will solidify over a range of temperature because there is no thermal arrest. Thermal arrest in Malay we call penangkapan haba. Jadi dalam ni tak ada penangkapan haba sebab tu dia solidify over a range of temperature 1085 degree Celsius. Next, we move to the binary eutectic phase diagram. What is eutectic? Eutectic comes from Greek word which is capable of being melted easily. Okay, what is eutectic point? Eutectic point indicates the eutectic composition and eutectic temperature. What is eutectic composition? Eutectic composition is the alloy composition that freeze at a lower temperature than all other composition. Then, what is eutectic temperature? Eutectic temperature is the lowest temperature at which liquid phase can exist, and this is the eutectic point. Okay. What is liquidus? Liquidus is the line that separates a liquid phase from a solid plus liquid phase region. During liquid system begins to solidify when the temperature cools to the liquidus temperature. Then, what is solidus? Solidus is the line that separates a solid phase from a solid plus liquid phase region. The system is not completely solid until it cools below the solidus temperature. Okay. What is solvus? When we look at the figure, solvus is in the green color line. Okay. Solvus is the line that separates a solid solution from a solid alpha plus solid beta. Okay, that's it. Eutectic. Eutectic is the horizontal line that connecting the intersection of the solidus and solvus from both sides. Okay. The eutectic temperature also is where the liquidus lines for both components meet. Okay. Next slide is the microstructural developments in eutectic system 1. Okay. Eutectic system 1 is for alloys for which C0 less than 2 Wt% Sn. When we look at the figure, the C0 less than 2 Wt% Sn is in the dotted purple color. Okay. For the result, at the room temperature, polycrystalline with grains of a composition CO. This. Yeah. For the eutectic reaction, for the eutectic system 1, is L equal to alpha plus L equal to alpha. Okay. Next, we move to the eutectic system 2. Eutectic system 2 is for alloys for which 2 Wt% Sn less than CO, and CO is less than 18.3 Wt Sn at this range. Okay. For the result, at the temperature in a alpha beta range here, the polycrystalline with the alpha grains and small beta phase particles. When we look at in the figure, the red dotted color is the beta phase particle. Okay. For the eutectic reaction for the eutectic system 2 is L equal to alpha plus L equal to alpha plus beta. Okay. Next, we move to the eutectic system 3. Eutectic system 3 is for alloy composition C0 equal to Ce. Eutectic system 3 form eutectic microstructure or lamellar structure. What is eutectic microstructure or lamellar structure? Eutectic microstructure is alternating layers or lamellae of alpha and beta phases. When we look at the figure, alpha phases is in the yellow color and beta phases in red color, and it repeated itself, alpha beta. Then we call it as the lamellae. Okay. For the eutectic reaction for the eutectic system 3 is L equal to alpha plus beta. Lastly, we move to the eutectic system 4. Microstructural developments in eutectic system 4. Eutectic system 4 is for alloys for which 18.3 Wt% Sn is less than CO and CO is less than 61.9 Wt% Sn at this range. Okay. For the result, alpha phase particles will blend together with a eutectic microconstituent. Alpha phase particle in the blue color will blend together with the eutectic microconstituent, the repeated layer of the alpha beta. Okay. The eutectic reaction for eutectic system 4 is called hypoeutectic alloy. Okay. What is hypoeutectic alloy? Hypoeutectic alloy containing Pb 30% Sn. Containing 30% Sn. Okay. On reaching the liquidus temperature of 260 degrees Celsius here, solid alpha containing about 12% Sn nuclear test. The solid grows until the alloy cools to just above the eutectic temperature. At 184 degrees Celsius here, from the tie line, we can see the solid contains 19% Sn and the remaining liquid contains 61.9% Sn. Yeah. At 184 degrees Celsius, the liquid contain the eutectic composition. Yeah, eutectic composition. When the alloy is cooled down, below 183 degrees Celsius, all of the remaining liquid goes through the eutectic reaction and transform to a lamellar mixture of alpha plus beta. Okay. Next, we move to the hypoeutectic and hypereutectic. The phase diagram must have a eutectic point, to have hyper-eutectic, and hypo-eutectic alloys. Okay, if an alloy, if the alloy composition places it to the left of the eutectic point, which is in the blue arrow on a phase diagram, then it calls hypoeutectic. If it is places to the right of the eutectic point, the red color arrow, then it called hypereutectic alloy. Okay. In hypoeutectic alloy, it contains alpha nucleotide, and in hypereutectic alloys, it contains beta nucleotide. Okay, that's all from us. Thank you.